next concept in understanding how a projectile causes damage to a target is known as cavitation. Now there's two forms of cavitation. The first of which is known as permanent cavitation, the permanent cavity. And so this is the hole that the projectile punches through the target or into the target as it travels and strikes that target. You can think of the permanent cavity as being akin to a sharp stick being pushed through that target. So a stick, the diameter of the projectile being pushed through that target is akin to this permanent cavity. And if that permanent cavity, if that projectile as it travels into or through a target strikes a vital organ, something like the heart or the brain, maybe the lungs, then of course this can be life-threatening. The second form of cavitation is what's known as a temporary cavity. And now temporary cavitation is formed by the energy that's dissipated into the target as that projectile passes into or through the target. So when that projectile hits a target, it starts to decelerate rapidly and lose energy. And that energy has to go somewhere, and it goes into this temporary cavity. So it starts to dissipate out from the permanent cavity of the bullet, from the path of the bullet. This energy wave dissipates and radiates out from that permanent cavity, and that in itself, that massive pressure wave that can emanate out from the permanent cavity as that energy is dissipated can cause a bunch of damage to tissues, to blood vessels, to organs that are around the site of the permanent cavity. Temporary cavitation is relative to the amount of frontal surface area of that bullet. So we spoke earlier about this mushrooming concept in hollow point bullets particularly, where a bullet starts to deform and its frontal surface area increases, it slows down faster, dissipates more energy into the target, that increases the temporary cavitation. But equally does if the bullet destabilizes when it hits the tissue and starts that process of yawing or tumbling. So it goes from going straight through and flying direct as it would in flight, stabilized by the air pressure and by the spinning motion from the rifling. When it hits a target, starts to destabilize because of that center of mass being slightly past the midpoint, wanting the back end of the bullet to flip around. The bullet can turn sidewards, and that increases the frontal surface area of that projectile in the tissue, and that increases the diameter of this temporary cavitation. It does more damage, more distance from the tract of the bullet. Looking at all of this theory as it applies to the real-time situation, let's start with analysing a low-velocity projectile as it strikes tissue. So say a 9mm round that we might find fired out of standard range of handguns or submachine guns. So this is categorised as a low-velocity round. And the standard projectiles that we see fired out of a 9mm handgun or submachine gun, they leave the muzzle at about 1200 foot per second. So the muzzle velocity is about 1200 foot per second. And they have a mass of about 124 grains, which equates to about 8 grams. A great way to appreciate the damage that a projectile does when it hits tissue, hits a target like a human, is to look at studies done on what's known as ballistic gelatin. So this is jelly that is calibrated with the density of human tissue, and by firing projectiles into that jelly and then taking slow motion imagery of that projectile striking the jelly and passing into it and sometimes through it, we can get an appreciation of what's happening within a human when they are shot. In this video, we see a standard 9mm round being shot into ballistic gelatin. And what we see is the typical reaction that will occur when that projectile enters the tissues of a human. So the projectile stays relatively straight on its path, so it has a tendency not to yaw or tumble. It will mushroom slightly as it starts to decelerate, so the forces of the density of that gelatin start to act on the front of the projectile and soften it and mushroom it, so increasing that frontal surface area. But 9mm rounds tend not to destabilize too rapidly within tissue. They tend not to yaw tremendously or tumble when they hit tissue. They tend not to fragment. They'll tend to stay intact, travel relatively straight, cause that permanent cavity, and then a small amount, relatively small amount, of this temporary cavity, which can be appreciated on the video. That's the pressure wave we see radiating out from the tract of the bullet and reverberating through the gelatin. So if we think of that entering a human body, this is going to be the damage to the tissues, the blood vessels, the organs that are immediately adjacent to the tract of the bullet. While we can see a bit of temporary cavitation, it's certainly evident on the slow motion ballistic gelatin video. In a low velocity round, so under 2000 foot per second, the main damage done by that projectile hitting a target is done by that permanent cavity. So that hole that the projectile pokes into or through the target as it travels. So there'll be a small amount of damage done by the temporary cavitation, but because of the relatively low velocity, that temporary cavity is limited. If a low velocity round happens to strike bone, it'll definitely do some damage. So when it hits a hard structure like bone, it tends to come to a stop and it will impart all of its energy into that hard structure. So if a low velocity round hits a bone, it's likely that it will fracture that bone, and at that point it may be that the bullet starts to fragment a little bit, break up a little bit. So it can certainly do some damage if it hits significant structures like bones, but nothing like what we see in the higher velocity rounds. A word of warning here: if you carry a 9mm or a handgun, particularly in a holster, this image here is of a 9mm that discharged in a holster tucked down the back of someone's pants. And it's a good illustration of the damage done at point blank range by a low velocity round, a 9mm round. So this pistol has activated, the projectile has punched through this person's buttock, and you can see the tissue damage done by that projectile. So that's the permanent cavity as the projectile from point blank range punches through that buttock. But you can appreciate that there's not a huge amount of bruising or tissue destruction around that permanent cavity. So even at that extremely close range, there's very little damage done by the temporary cavitation of low velocity projectiles.